of wrapped up the first kind of chapter there on intermolecular forces and materials, kind of that kind of stuff. For those of you guys who have been kind of following along in the book, obviously we didn't go through everything in there. Not that it isn't interesting, I guess, but you know, the book kind of talks about things like liquid crystals and how they work, and then they talk about crystalline solids and lattices and all these kind of things. And you know, that stuff's useful and it's nice. And if we had an engineering program here, we'd go through that stuff because it's important to know and understand how density and packing efficiency and that kind of stuff is useful. But you know, we don't really have that here. Not really. We don't have that here. So you know, I kind of make some decisions about what's important to invest your guys' time in. So it's there, we're not going through everything, so what I would say with that is just kind of follow along with the notes in terms of what I spend my time focusing on versus necessarily what everything that's in the book there. Besides, you guys have the book, and you guys can follow along for what you guys need with that anyway. Let's see, so we finished up that chapter there. We'll have a quiz this week, probably on Friday. It'll be online kind of thing there. I'll give you guys the instructions and all that kind of stuff ahead of time, so you guys can get prepped for what you need to do with that. But it'll basically just cover the material that we have discussed in class. Is kind of what it is. Let's see, what else? Oh, I think I finally figured out the technical hiccup there with the video, so they should be going up. Although it now takes me 8 hours to get one video uploaded. It's fantastic. So yeah, the internet here is restricted. So anyway, it's all good. It'll happen. It'll be up there. I'll be chugging through them as I can, as regularly as I can. So we'll keep moving along with that stuff in case you guys have to miss class, or as I imagine in about 6 weeks or so, ground zero will happen again with everybody swarming to quarantine, but we'll see how it goes.
Why are you estimating 6 weeks?
Well, it takes about 2 weeks to manifest and for it to kind of spread around to a reasonable number, right? So don't worry, I've got a running back going, so we'll see how it goes. I was off by a week in the fall semester, so I revised my strategy this time, but it's all good. So anyway, the next chapter here. We're going to be looking at some specific applications of solutions. Now, we talked in the first semester about calculating molarity, and we did some computation, I guess, or calculations with how we can do or calculate the moles of something in a given volume. We talked about concentration and molarity there, and how to convert between moles and molarity and volumes and all these kind of things. And so you're going to be bringing a little bit of that idea back, but we're going to talk about some of the, I guess, shortfalls of molarity, and we're going to introduce a new way that we have of measuring concentration, known as molality. Now, we'll introduce this, and we'll never use it again after this chapter. Fantastic.
It's being used in lab this week.
Yeah, I know. Like I said, I don't know. While I'm up here, and you guys have to listen to me because you don't have a choice. I'll rant about certain things. You know, some of the items that we go through in Gen Chem. I don't really know why they pick the things they do. For what it's worth, a little bit of a peek behind the curtains. It's not just me, right? It's not like, well, I feel like talking to them about solutions, right? There is a, kind of a set curriculum that's a national standard that we try to follow here. So it's not like I make the decisions. What I'm really saying is direct your ire somewhere else, right? Don't, it's not, no, but anyway, so we will talk about concentration and molality. And we'll learn about colligative properties. Hang on just a second, Rachel. So we'll talk about colligative properties, specifically freezing point elevation and boiling point, freezing point depression and boiling point elevation, which I think is what you guys are doing in the lab this week, right? Yeah. Now we'll talk a little about, where we will start today I think is kind of a little bit of a review from a lab that you guys did last semester too. So we'll get through this stuff, and I know. Wait, when are labs for you guys? Monday, Tuesday? Tuesday, Wednesday? Okay. So hopefully, I don't know, I don't think we're gonna get the colligative properties for my Tuesday group here, but we will definitely get there by Wednesday. So if Dr. Tom gets mad at you guys, just tell him to come talk to me or whatever, and we'll let him know. I'm trying to keep pace as best I can, right? So, but we'll get there, I promise. And if we do end up falling a little bit too far behind in lab, then we'll adjust as we need to, so that you guys aren't kind of left out in the dark there. Okay. But I think that's kind of the review, the intro there for solutions. We'll do a little bit of math, a little bit of concepts, and tie it back to what we just finished up. What's up?
There's no chapter 13 in the lecture slides.
Yeah. Now, did I put the wrong number in there or something?
Oh, wait, hold on. No, I think it's fine. It says 14.
Maybe I just put a typo somewhere then.
Yeah, okay, never mind.
Yeah, a previous version of the textbook had different chapters, so maybe you guys will run into a typo here and there as things kind of move around. All right, anyway, so we're going to start with something very similar or familiar if you guys have your previous notes there. Just, the definition of a solution and a solvent and a solute and all these kind of things, right? This is all stuff that's been introduced before, right? So we know about a solution, right? A mixture of substances. A solvent's the thing that's there in the greatest amount, right? And we can make examples about when you make, Kool-Aid or something, right? You're dissolving sugar into water with some food coloring. And each of those components that's in the Kool-Aid has a certain concentration that we could measure within that solution there, right? How much food coloring, how much sugar there is, how much citric acid, all these different parts that are in there, right? So a solution doesn't just have to be one component, right? There could be more than one thing that's all in there, right? So that's all I'm trying to say with this stuff here, right? Now, these two parts at the bottom is where we kind of tie in a little bit more from what we talked about in the previous chapter there. And we'll mention this a little bit here. And again, we're going to come back to this idea of dissolving things later in the semester in a different chapter when we talk about equilibrium, okay? So, but the idea is this: well, how do we know, or how can we predict, or how can we maybe take a scientific stab at how or whether something's going to dissolve or not, right? And so it all comes down to these intermolecular forces here, right? Why is sugar so soluble in water, right? That's basically the question that we're going to try and get at there, right?
Because hydrogen bonds?
Yeah, right? It's because we're talking about similar properties in what we're trying to dissolve, between the solvent and the solute, right? So if you have a lot of hydrogen bonding like we see in sugars, right, any kind of sugar, right, those are going to be extremely soluble in any kind of aqueous solution, right? So we have very polar compounds that are soluble in other polar solvents. That's what we're getting at with that. So that's kind of, whenever somebody asks you, will this be soluble, that should be kind of the way you approach this, right? What type of intermolecular forces are present in the solvent, and what type of intermolecular forces are present in whatever you're trying to dissolve. Now, is that going to be a perfect prediction of solubility? No, right? Because if chemistry was easy, then I couldn't meet my quota of failing some of you guys each semester, right? So I have to make it very difficult and hide information. No, I'm just kidding, right? Yeah, so I'm kidding. No, but, right, so is this going to be a perfect prediction of things? Of course not, right? Because, remember, we talked about the solubility rules in the first semester, okay? And if you recall, the first rule that we learned is that any group 1A metal, right, is going to make a soluble compound, right? So anything with lithium or sodium, potassium, right, these kind of things are going to make soluble compounds. And that's somewhat true, except there's some very obvious exceptions to these rules too, right? And we'll talk a little bit about what that means. Because if you think back about these rules, they just said something will be soluble. Okay, what did it not talk about? How much of it is going to be soluble, okay? So that's what we're going to learn about a little bit later when we talk about equilibrium. We're going to introduce the topic here in a little bit just about a saturated solution, right, versus an unsaturated solution. And we'll kind of continue to develop this idea as we go through. But solubility is extremely important, right, extremely important in not only chemistry, right, but if you pretty much think about any biological system, right, how much of a sugar is dissolved in your blood is pretty important, right? How much oxygen is dissolved in water is important to aqueous, aquatic life, right? So this idea of solubility is an extremely important idea as we go through any of these different disciplines, right? So, but anyway, for the immediate purpose, think about your intermolecular forces and how those two can kind of relate together there, right? So we can have solutions in all three physical states. We kind of just emphasize and really hit home in this class about what's going on in solution, right? But we have given the example before of basically air is a solution, right? We have something that exists in a greater quantity, nitrogen, right? And then we have all these other things that are kind of dissolved around in there, right? So that might be an example of those things there. Obviously, sodas are gases and liquids, and like gas and a solid. We could talk a little bit about porous materials there and how we store things, and not just hydrogen, but there's also, I guess, for a little bit of a this and that. So we know there's been a recent push for carbon capture systems, right? So how can we remove carbon dioxide from the air and make the world better is what they claim, right? So here's a question. Can we get CO2 out of the air? Sure. You guys can do it at home, right? It's really not that hard to do. You get some drain cleaner, you put it into a cup, right? You make a fairly concentrated solution in water and just sit it out. And what you'll see after a couple days, you'll see some white precipitants start to form, right? That's just the hydroxide that's in the aqueous solution reacting with the CO2 that's in the air, and it makes some kind of carbonate species, okay? So not too hard to do. Do you know what the problem is?
Then you have waste.
Well, not just waste, but what are you going to do with it once you capture it, right? So when I was working in Tennessee, I was working at the Department of Energy labs, right? And so this is a big focus of their stuff, right? Carbon capture, all these kind of things. And so there was a university, I believe it was West Virginia University. They were trying to study where we can store gaseous CO2 once we capture it. And so their thought was to basically just pump it underground, right, into these old caverns that were formed from mining and these kind of things, right?
That's really.
Well, it's actually not a bad idea. Nobody else is using it, right? So it's a big open space underground. What else are you going to do with it, right? And so, but anyway, what they were studying is just how well the CO2 dissolved into the rocks, right? How porous are the rocks? How long would it take for it to diffuse out? These kind of things, right? So we don't think about it too much, right? But gases dissolve, so to speak, into solids is something that's becoming more and more and more important these days as we go to these kind of like carbon capture and alternate fuel sources, that kind of thing. But anyway, I don't need to read through the whole thing here. You guys can kind of read through that on your own. But understand that what we're talking about when we deal with concentrations and solutions and dissolving, any of these different states and phases exist, right? All right, so there's the name of the game there at the top. How do we predict these interactions? Well, the trite saying is like dissolves like. Polar compounds are going to dissolve in polar solvents. Non-polar compounds are going to dissolve in non-polar solvents. Right, and we could talk about the example of oil and water, right? Now we could talk about two separate things there, maybe to come up with a bigger discussion, right? Why doesn't oil dissolve in water? Well, to answer a question like that, what do you need to know? So if I have the question, why doesn't oil dissolve in water?
You need to
what
know.
information do you need?
You need to know what intermolecular forces.
Mm-hmm. So we'd have to know the intermolecular forces in the oil that we're talking about and in the solvent, the water in this case. What else? Yeah.
Polarity, but.
We'd have to know the polarity, right? We'd have to know is water polar, is oil polar? What else? Or how would we determine polarity? What information do we need for that? We need to know the electronegativity, so we have to know what atoms are present, right? What's the composition of these individual, of the individual components that we're trying to mix, right? What else do we need to know for polarity? Not just the atoms and the electronegativity, but the geometry, the shape of these things, right? All this stuff is important when it comes down to predicting the potential solubility of two things, right? So if you have all that information, what you would find is oil is very non-polar. It's this long, straight alkyl chains, right? And they just don't want to mix that well with water, is what it is. Water's very polar, small molecule, wants the hydrogen bond with things, and oil's not going to do that, right? Now, you guys know, right, that oil floats on top of water, right? Now, why would that be the case? What's that?
Lower density?
Yeah, so density, right? So this is something that we kind of skipped over in the last chapter there, right? But we could start to talk a little about how we could predict density of solids and liquids and all these kind of things. And that is a property, or density is a property that's based off of the geometry and the shape and all these kind of things also is what it is, all right? So all these things kind of tie together to ask a very, maybe innocuously simple question of, is something soluble, right? So maybe we just spent like the last 5 minutes just discussing the individual topics of how we could even start to predict solubility. And then it goes back to the point that I just made. Is it always going to be 100% accurate? No, right? But these are the things that if I ask you, hey, do you think this would be soluble? What would you need to do? Check your electronegativity, draw your Lewis structure, check the intermolecular forces, right? And the more similar the solvent and the solute are, the more likely they are going to be soluble in each other. Got it? That's all it is. Yeah.
So, don't hydrocarbons have hydrogen bonds then?
Aha. A very interesting question. So this is a quick this and that. So I recently submitted a paper, right? And in the paper, I was looking at a new compound that had been made, and I said, hey, look, there's hydrogen bonds in here. It got rejected, right? Because it's not classical hydrogen bonding, right? So I had a big argument with the editor about this, right? So, immediate answer, in my opinion, yes, right? In a lot of other people's opinion, no, right? Because what does it mean to be hydrogen bonding? Now, I gave you guys a definition, right? And I said, when hydrogen is bound to nitrogen, oxygen, or fluorine, and then it can interact with another electronegative atom. Well, what do we know about the electronegativity of carbon and hydrogen? We say that they're about equal, right? In reality, that's not the case. And anytime you have a disparity of electronegativity, you're going to end up having some form of partial positive and negative. So the long answer to a very complex question there, or let me say the short answer to a very complex question is, technically there's a lot more hydrogen bonding than what we're talking about. But the definition that we're talking about with hydrogen bonding is those 3 specific instances. That doesn't mean that hydrogen bonding doesn't exist in other things. It's a antiquated definition, maybe, might be the way of saying it. That's just what it's come to represent, even though it's a broader scope than that, right? So, that was a lot of blah, 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 blah. The answer is yes, it exists, but don't call it that, maybe, right?
Okay, so hydrogen bonding is, we're only calling it that when it's bonded to nitrogen,
Oxygen and fluorine. Yeah, the 3 most electronegative atoms, yeah.
okay. So we're just ignoring carbon.
We don't ignore it. We understand that why would hydrogen bonding only exist in nitrogen, oxygen, and fluorine? Because there's a big disparity in electronegativity, right? And that's where the ambiguous definition might come in, right? How big of a difference does there have to be for this to happen, right?
Okay.
Anyway, so why does this happen, or what do we need to take care of, or what do we have to do? Right, so maybe this is a decent representation if you guys can kind of look through all the different word jumble that's up there. So how do we start to dissolve things here? Well, if we think about it, right, so we have hydrogen bonding in the initial compound that we're trying to dissolve, so ethanol in this case, right? We have this hydrogen bonding in the water, so if I want to dissolve ethanol into water, what I have to do is break apart the hydrogen bonding in both cases. Okay, so I have to break apart the hydrogen bonding in ethanol, I have to break apart the hydrogen bonding in water, and then when I put them 2 together, right, I start to make new bonds between the water and the ethanol that's in there. Okay, so that's what this picture is trying to show you guys, right? What's the physical process that happens when you're trying to dissolve things? Do you guys get what I mean with this? Okay. What I'm saying is when I dissolve 2 things together, there's going to be a rearrangement, a shift of the molecules on both components that go in there. The ethanol has to basically float apart, the water has to float apart, and then they can come together and rearrange themselves in a new way. You guys following along with this? You guys are okay? So oftentimes we're just like, yeah, we just mix the 2 things together and there it is. But there's an energetic cost to dissolving something. Now you guys already know this too, and I'll show you guys, or I'll remind you guys why I'm submitting, okay? But all I'm trying to show you guys here is we have to move these apart, and then they come together in a new way. And if that happens, then we can dissolve things, okay? A little bit of terminology here, just for what it's worth. Miscible and immiscible liquids, right? Miscible liquids dissolve in our proportions. Sometimes miscible things are called infinitely soluble, although obviously that can't be the case, right? So immiscible, right? Just we form two separate layers. This will become really, really, really important in organic chemistry, right? In organic chemistry, we're going to use the principle of miscible and immiscible liquids quite a bit when we do the synthesis in the labs there, right? So, very important concept. And just for what it's worth, I'll give you guys a preview here real quick. This slide right here covers one of Dr. H's forbidden organic questions, right? Because you guys answered the question already. And then something happens, I don't know, right? Between the end of this semester and maybe over the summer break, by the time you guys come back for organic, you guys forget what density is. And so, and I asked the question in the organic lab, how do we know which liquid is going to be on the top or the bottom? The answer is, right? So, you guys, right? This is important. This is the most important thing I'm going to teach you guys all semester, right? Don't ask Dr. H what density is in organic. I'm joking, but the idea, hang on just a second, Rachel, right? But the idea is this, right? Just so if you guys see something described in the literature or in your book or whatever it is, right? Miscible does have a definition, but we're going to put the limit on that this semester, right? We're going to talk exactly what the maximum solubility for something can be, right? So we'll be able to calculate that, okay? What's up?
So, are these, okay, I can word it, I swear. Do the captions indicate that, like, in the first picture, the heptane and carbon tetrachloride, they're mixed together and forming like a homogeneous solution, and then when you mix it up, they separate? Why does that happen? Why don't they just stay in the same?
Why don't they, or why can't they, or why shouldn't they? Right? The answer is all three of those. Right? Again, it comes down to just what's going on. Right? We have the heptane and the carbon tetrachloride together there. How well do they like each other? Well, you'd have to ask the question, what's electronegativity, what's the geometry, right? All these kind of things, right? So they could just be miscible together, and then once we kind of add some energy into it and rearrange everything, then they're going to separate back out. Right? So remember on the previous slide, we said that when we start to mix things together, we have to move things apart and bring things together. Right? If we add energy into that, we're going to start to rearrange things again. And it could be that we add enough energy into that to break those apart and they end up layering like this.
Okay.
Does that make sense? Okay, I'm not gonna spend too much time here, but you guys will notice a blue arrow on the right-hand side there, right? So when we're talking about whether something's miscible, can we dissolve it? Take a look at intermolecular forces. But not everything has just one dominant intermolecular force, right? That's the other point for you guys to start to take a look at here, right? That's why I give you guys this slide here. As we add more carbons and hydrogens to our compound, right, the hydrogen bonding component becomes less and less significant, right? And so we see less and less solubility in water, okay? So then the question might become, well, at what point do we hit that balance of, hydrogen bonding being more important or less important, okay? And that's all I really want to show you guys here, right? So we can just count how many carbons there are all the way from 1 in methanol to 6 in hexanol there. And at some point, the hydrogen bonding can't compensate for those other intermolecular forces that cause it to not be as soluble in water, okay? Oh, sorry, yeah, one more important thing here. So notice on the top right-hand side there, I give you guys solubility at a specific temperature. And that's going to be important for two things. We'll talk about a system where the solubility is independent, right? Or excuse me, the concentration is independent of temperature. Because as I increase the temperature in something, everything will become more soluble, except, and we'll talk about that, right? But paying attention to the temperature is going to be extremely important.
Why does solubility grow with temperature?
Why?
Yeah. Oh, because energy, okay.
That's all good. Okay. So, and this is just kind of a summary of those, of the last couple of slides there, and maybe a different picture down here at the bottom of how we can dissolve a solid into a liquid here, right? So again, making those forces, having the appropriate amount of energy. Remember, whenever you make bonds, right, whenever you make bonds, you're going to release energy. Whenever you break bonds, it's going to take energy to do that, right? So the question becomes, does it take more energy to break the bonds apart, or do you make more energies for the stuff to come back together there? Okay, and that's the kind of stuff we can start to put numbers on this semester as we move forward. Okay. Now, if we take this very same picture, okay, does everybody understand what I'm showing you guys in this picture here, right? Just molecules moving apart, coming together. Okay, I'm going to take that very same picture. I'm going to make it look a little bit scarier. Okay, because now I'm starting to put enthalpy values with this. And there's no nice, pretty colored, spheres there to represent individual things, right? This is the exact same picture there, okay? Now, a couple things to remember here. When we're dealing with enthalpy, remember that it's a state function, right? And a state function just means it doesn't really matter how we get to the final value, just that we get there, right? We can take different paths to get there. It's in mathematical, though, we can say with that, it's the individual steps all add up to be the total, okay? So again, if you'll notice over here, I have everything separate. Over here, I have everything together, right? So if you follow along with the slides here, I have to move the solvent apart, right? I have to move the solute apart, and then I can bring everything back together, okay? Does that make sense? Right, so I'm showing you guys the exact same thing there, but now we can calculate an energy, at least one component of energy for this, which is the enthalpy, okay?
So the energy affects the solvent before the solute?
What do you mean?
It's showing like it's, okay, so is that energy happening at the same time? Or is the energy going in to separate the solvent before, like, it separates the solvent?
We're just kind of taking pictures of individual parts, right? So this is not, there's not just, you could think of this as these are in separate beakers or whatever, and then we mix them together. And depending on how much energy is present, then this all happens,
okay.
Right? So it's just individual snapshots.
Okay.
Yeah. But what you can notice is that sometimes we can have endothermic or exothermic enthalpies of solution, right? But you guys already know this too, right? What did you guys did last semester, right? You guys got your scientific coffee cups, right? Mm-hmm. And you dissolve different salts into the water, right? And you measured the temperature, right? And some of them got hot, right? And some of them got cold, right? What were you guys measuring at that? The enthalpy. Now we could take that enthalpy that you guys calculated and start to break apart the individual components if we had the information for that. That's all it is, right? So same thing that you guys are doing last semester now, just looks a little bit scarier maybe. But here's something new that, again, I'll introduce here and we'll come back to in a couple of chapters. Yeah. So if you'll notice, what I've been mentioning is that enthalpy is a component of energy for a system. There's different types of energy we can measure and we have to account for and that we have to calculate. And entropy is another one of those. Now, entropy is one of those terms that I think you guys have probably heard colloquially, right? We kind of tend to think of it as disorder or mess and that kind of thing, right? And that's true-ish, okay? But if I ask you guys to calculate the mess of something, could you guys do that?
Yes.
Maybe, right? Right?
My mom says my room is classified as a tornado disaster zone.
Okay, so we'll measure that as 1 Rachel unit of mass. Okay, right? Right? But entropy is just a calculation of energy. Okay, and so it'll be another component that we'll talk about as we look at the total energy of a system. Okay. Now I'm not going to put we're not going to put too much scary terms with it here in this chapter because we'll talk about it when we get to the chapter on Gibbs-free energy and whether a reaction is spontaneous or not. Okay, there it'll become really important. And it'll be one of these seminal equations that everyone's expected to know out of general chemistry, right? How do we calculate the spontaneity of a reaction, that kind of thing, okay?
What would spontaneity be in that case if they avoid just...
Great question. Hang on to that question until we get to that chapter, right? Because I'll give you the definition for it. All right. So Anyway, what we start to learn then is we have to take into account both the enthalpy of solution and the entropy. And each one of those we can put a value with. Okay, now we talked about enthalpy last semester. We introduced it a little bit in the previous chapter, and we'll get to entropy later. Okay. Now the other thing we have to take into account is just how much of this stuff can we put into solution. Okay. So we have a couple of terms here. We have unsaturated, saturated, and supersaturated. Okay. Now, if we want to make a little bit of a simpler definition with these things, starting at the top there, if I'm unsaturated, this means I can dissolve more of my stuff. That's all it means. Okay. Saturated is you've hit exactly the point where you can't add any more into it. And then supersaturated is you have more than the equilibrium amount dissolved. Okay. Now, equilibrium again is one of these terms that we've probably heard colloquially introduced in some of these other realms of science or rhetoric, whatever you want to say. Okay. But again, this is something we're going to be exactly calculating. Right. Now, here's what I want you guys to recognize or start to pay attention to. Whenever I talk to you guys about equilibrium, you're going to see me have things like Q and K. Okay. Q and K are inherently things that we will learn about when we get to the equilibrium chapter, and we're going to be able to calculate the equilibrium constants. And those equilibrium constants are going to tell us whether we're at a saturated solution or a supersaturated solution, those kind of things. Okay? So the Q and the K stuff here will become more evident later on. What does this information tell us at the moment? Right? As we increase temperature, we increase solubility. Right? And this is useful for us when we're trying to predict or when we're trying to do a recrystallization in the lab, right? And so this is a technique that you guys are going to learn in organic chemistry, and it's all based off of solubility and temperature, okay? This is a key component to understand here. Solids, as you increase the temperature, you're going to increase the solubility. I can't think of an example where that's not true, right? Pretty much every solid that I've ever seen, as you increase the temperature, gets more soluble.
So would it break your brain if you found a solid that wasn't soluble when you raise the temperature?
No, my life doesn't revolve around that. That's not my tipping point, right?
Right? Interesting.
Yeah, no, I'm sure there's something. We don't run into it practically speaking, right? But anyway, so there's your three terms there for you guys just to pay attention to as we're going through. Right? All right, if we take that exact same idea here that we just talked about on the previous slide and put it into something that's a little bit more, let's say, Gen Chem 2-ish, okay? So solute, right, the thing we're trying to dissolve, plus our solvent, goes to make a solution, okay? In the book, I think it talks to you guys about solute plus solvent, and they give you the dissolve and the crystallized thing there. Now you guys notice I have an arrow pointing in two different directions, okay? Here's the next thing to start to pay attention to. Right? When you see an arrow pointing in two different directions, I am telling you that there's an equilibrium that's established. Now, we don't know too much about that yet, but we'll get to it, okay? But pay attention to whether you have a single arrow pointing in one direction or an arrow pointing in two separate directions there, right? One of those indicates an equilibrium, which is the two-pointed arrows, and the other one is just kind of a single reaction happening in one direction like this, okay? All right, and here I just pulled these from the textbook. These exact definitions, you guys are welcome to copy them down if you want to or not. They're in your book there. I'm not gonna spend too much time here reading them out, right? But you'll see we start to introduce these ideas in terms of equilibrium and saturation and how soluble they are and that kind of thing. Okay.
So hold on, why does crystallization happen?
What's the opposite of dissolving something, right? It precipitates out of solution again.
Okay.
Yeah. Yeah, we already talked about that. Okay, so here's kind of one of these quintessential examples of what happens. We used to do chemistry demos. Officially there's a chemistry week, right? And it happens to fall whatever week in October has the week of October 23rd in it, right? Because it's 1023 6.022. Avogadro's number is on 10 23rd. I know. I didn't make this up, but that's what it is, right? So we used to do a bunch of like chemistry demos for the kids and stuff at the mall and these kind of things. And this was always one of the stuff that we did, right? You make a saturated solution, you add, the book talks about a seed crystal in there, and all of a sudden everything starts to crystallize out with it, right? So we introduce something that pushes the equilibrium of the thing being dissolved versus crystallizing, and it starts the crystallization process, right? It starts that, I have to be careful here, I'm gonna call it a reaction, it's not really a reaction, right? But it starts that processing happening, there's what it is. So as soon as I disturb the equilibrium, something happens. And we'll talk about how we can predict whether the equilibrium is going to be disturbed later on, right? But I always find this stuff cool. You guys can actually do this at home if you try to freeze like soda water. If you put soda water, like, you know, a fresh bottle of it in the should I give you guys ideas?
Yes.
But if you freeze like soda water and then you take it out and you quickly crack it and tap it on your countertop, you can actually freeze the water instantly as all the CO2 escapes, right? Because it remains a liquid with the CO2 dissolved, but as soon as the CO2 comes out, then you can instantly crystallize the entire bottle of it. So there you go, impress your friends, impress your neighbors, right? So going back to this idea here real quick, right? How do we then kind of picture what's going on with an ionic compound, right? Remember when we talked about the solubility of ions and all these kind of things, we talked about lattices. Well, excuse me, we didn't really talk about lattices, right? Lattice is just how these things look in the crystalline state. Who cares about that kind of stuff, right? Just as what we learned about with molecular geometry, right? So there's tetrahedral and trigonoplanar and all that kind of stuff. There's different lattices that ionic compounds can adopt, right? And there's certain names for those. Now, that might sound really cool and important, and it is, okay? But it's not something that we need to chat about here, right? So when you're seeing the thing about a lattice there, just kind of think of it as ionic geometry, if you want to think about it, okay? Rather than molecular geometry. But there's a cost to break apart the lattice, and then there's a energy that comes back when we can reform the hydrogen, or excuse me, the water interacting with the ions there. And to come out of this, right, there's a couple of different terms that the book mentions. Lattice energy, right, the energy to hold everything in the lattice there, overcome it, and then the enthalpy of hydration. Now this is something that is kind of cool, right? So if you remember, just a couple of minutes ago, I said that there's, anytime you make a bond, there's a release of energy, right? So where does that energy come from, might be the question, right? Well, this is one place that it comes from, right? The enthalpy of hydration. So remember, right, the rule was like dissolves like, okay? If water is a polar molecule, that means it has negative ends and it has positive ends, right? Well, if we put something ionic into solution, right, the ionic compound has very positive things and very negative things. Okay, that's what the definition of an ionic compound is, right? Something negative, something positive, right? And so if we have something like a sodium cation in solution, we're going to see that the oxygen atoms arrange themselves in a specific manner around that cation there. Okay? Now, a couple of things to notice about this, okay? This is something good that happens. We have something positive and interacts with 6 negative things around it, right? 6 of these water molecules are surrounding it. But there's some consequences to that. The first consequence is it releases energy, okay? And when we tend to dissolve something like sodium hydroxide, you can actually boil water, right, by just dissolving sodium hydroxide in it, okay? And so you might think that that's pretty cool, and it is, but it's a problem when I go to prep the lab for you guys, because when I have to make sodium hydroxide, it takes forever. So I have to add the water in, and it gets really, really hot, right? And then I have to wait for it all to cool down before I add more hydroxide and these kind of things.
So it's kind of like when you're shocking or adding calcium to the pool and it gets like really hot and you have to make sure your dog doesn't jump in and die?
Yes. That's exactly what it is. I don't know, what did you say, calcium what?
I was taking care of our pool for a while, and the people at the pool store were concerned I was gonna kill myself or something, so they were giving me extremely specific instructions on how to add the different chemicals to the pool.
It's probably smart, right? You're making solutions here, right? And some of these things are, calcium chloride is also very, very exothermic when you dissolve it.
Yeah.
So that might be what you're adding here, right?
Yeah.
But anyway, so that's great. Fine, we can dissolve things, but there's something interesting there. So you have a release of energy. Where does that energy go when you're dissolving something?
It's used to form a new thing.
What new thing?
That?
So you have a grain of sodium chloride, right? Or whatever. You drop it into a beaker of water. There's a release of energy when that happens. Where does that energy go? Into what? Into the unknown? Is that what you said? No, we know exactly where it goes.
Oh, energy's released when they're made, when bonds are made?
When the intermolecular interactions are made, yeah. Where does that energy go?
The surroundings?
What's the surroundings? What is immediately surrounding that sodium cation in that water?
Probably more water.
Aha, you guys got it? Remember, I just told you that. I said if I put enough sodium hydroxide into water, it'll start to boil the water. So where's the energy going?
To the water.
Into the water, right? We're increasing the temperature of the water. What happens when I increase the temperature of my solvent?
You can dissolve more stuff.
Solubility increases too, right? So remember, there's kind of this, what's the word I'm looking for here? The
Vicious circle?
Yeah, but what's the sign? This positive feedback loop here, right? So I add in an ionic compound, it increases the temperature of the water so I can dissolve more of it, which causes more energy to get released, right? So there's kind of this positive feedback loop there is what it is, right? And so we have to be careful when we're making certain solutions because we can have some of these issues of making things over-soluble and then precipitating out when it cools back down. But that's also a good thing, okay? Great, so what? We release enthalpy, or excuse me, release enthalpy. We release energy, right, from the enthalpy of hydration when we dissolve an ionic compound. Thanks, okay? So there's that. I don't need to read a wall of text for you guys here, but this is similar to what we were talking about in the previous slide there where I broke enthalpy down into individual components, okay? There's an individual energy component to make the enthalpy of solution. That's all I'm showing you guys here, right? So the stuff up at the top there. The cations have a different enthalpy than the anions would, right? And there's also the cost of the lattice energy being broken apart, right? And that starts to explain a little bit about the hot and the cold packs there, and that's kind of what you guys did last semester. Yeah, what's up?
How do the hot packs work where you press the button? I'm assuming that, you know, that's kind of what kind of reactions happen. You press the button and something like gets triggered and the entire thing like crystallizes and gets
Yeah,
triggered.
so usually you have like a little glass vial of your ionic compound kind of surrounded by water, like in the plastic bag.
Well, no, these things are reusable, like the button.
Oh, that's just like, you know, probably some rechargeable battery or something, just passing a current through a wire. Right?
Really?
Probably.
Because you can microwave.
Look, I'm flattered that you think I know everything. I genuinely am. But I'm just a dumb chemist, right? I can just make, you know, simple hot and cold packs. And I would imagine just like a battery passing a, you know, current through a wire, that kind of thing, similar to what your stove works, right? But cool. Anyway, so individual energy components add up to be the overall energy, right? But there's another thing we have to pay attention to, okay? And there's our entropy, okay? So the change in entropy of the lattice is greater than 0 when the lattice breaks down, and the enthalpy of hydration is less than 0 when water molecules surround the ions.
Is it okay to go cross-eyed?
Sure. Okay, so what in the world is it saying here? So up at the top there, there's an increase in entropy when I break apart a crystalline lattice. I'm making things more disordered. Okay? Still with me?
Mm-hmm.
So I make things more disordered when I break apart a crystal. Does that statement make sense?
Yeah.
Let's think here for a second. What does it mean to be a crystal? Well, we have this infinitely repeating unit of the same molecules being mathematically tessellated over and over and over and over and over again. Right? We have the same repeating pattern of a molecule over and over and over. It's very ordered. It's very structured. Okay? That's what a crystal is. Now I take that sodium chloride crystal and I put it into water. Remember what I showed you guys in the previous pictures. What happens to it when I put it in the water?
Separates.
It starts to break apart. Is it infinitely repeating anymore?
No.
No. Right? Is it ordered anymore?
No.
No. So we increase the disorder, or what we'll say later on is we increase the number of accessible energy levels. Okay?
Huh?
But that sounds scary, so we just call it disorder. Okay? So you guys with me on that one?
Yeah.
So I create disorder by dissolving something. But what does it say in the second part there? I remove disorder. I make things more structured. Right? Delta S is less than 0. Why? What's causing a decrease in entropy? Yeah.
Because when
If this is about your dog, it's going to be wrong.
okay. Because when the H2O molecules attach, they form like a new pattern, and it's not kind of repeating and stuck together in the same way, but there is a new order.
Aha. Right? So take a look, right, at this slide right here. Okay? Do you guys see how the water is arranged around that cation there?
In an octahedral.
In an octahedral geometry. Right? Now remember, we haven't talked too much about octahedral, at least in my section, we didn't talk too much about octahedral geometries.
They were
Right.
scary.
Yeah. Right? But there's an arrangement for the water molecules now. Those water molecules are stuck around those cations. Got it? So we're decreasing disorder. Before the ion was dissolved, those water molecules were happy and free. Right? They're tumbling around, they're floating around, they're sliding past each other, they're existing in the liquid state, right? But as soon as I put an ion in there, they're going to be attracted to that positive charge. And they're going to want to stick in that same pattern around that cation. So we order the water. Okay? What's up?
What is entropy again?
Right now we'll leave it at the definition of disorder,
Disorder?
right? And we'll put a calculated energy value to it, right? But that comes a little bit later. So does this make sense then why we decrease entropy? Right? If we cause these water molecules to arrange in a specific way, we decrease the entropy. Yeah.
What if you added a bunch of salt to water and you heated it up enough that it totally like broke down and stuff, but there wasn't enough water to complete the octahedral on all of the sodium and chloride
Right.
ions?
So what you're talking about there is making a saturated versus supersaturated solution, right? If you can't dissolve anything else, it's not going to go into solution. You're just
Right.
going to add, it's just going to
But
down
so,
to the bottom, right?
so in a supersaturated solution,
Then everything exists, and you could think of it, everything existing in the same coordination, right? Everything has the same number of waters around it. Now there could be an equilibrium where there's different forms of hydrated ions, right? Sometimes it exists with 5 versus 6, right? For instance.
okay.
Yeah.
Can you like say again what energy is being released when it becomes hydrated? Because like I thought it like forms like a bond, and
It does. Yep.
so like
There's an energy gets released when you interact something negative with something positive, right? That's a good thing that happens. That's all we're talking about there. Okay. Did that answer your question, or?
kind of.
Okay, so what you're really saying is no, so that's fine. So what, maybe ask your question again, or what else are you looking for there?
So like I don't know, just like what energy is being released?
What
From
energy?
where? Yeah.
So each molecule has an individual internal energy, right? And when they come together to form a new bond or whatever it might be, right? If they both come to let's say a good agreement, right? Someone's brain is full, all right. Right? So if they both come to a good agreement, there's a lowering of energy of the entire system there together. There's an individual measure of energy for both of those. When they come together, then there's something new that happens,
Okay.
right? Now, I think maybe what you're asking is all energy the same, right?
Yeah. Kind of.
There your answer is no, right? So, but that's a very, very, very complex question which has multiple semesters kind of associated with it. It's a very good question, right? Because where is that energy stored, right?
Yeah.
That's another question, but very, very, very good
In
question.
bonds, right?
Sometimes, right? That's a great place where energy is stored, but also if you think about it, if a molecule is spinning around, there's a certain energy that gets released if we stop it from spinning.
How would you stop it from spinning?
By binding it to something so it can't spin anymore, right?
Wouldn't it just bring that thing into its spin though?
No. Sodium's probably heavier than, no, sodium is heavier than water, right? So There is this argument about momentum and all these kind of things, right? Anyway, so if we go down to here, just a quick statement there. So your +1, -1 ions, your mono cationic or mono anionic ions tend to be soluble. So what's the immediate follow-up statement to that? What happens as we increase the charge?
They become less entropic or more entropic?
Why? So let's think about this for just a second. Again, back in Gen Chem 1, one of the rules that we learned about solubility is that phosphates, right, phosphate, which is what?
PO4?
For
3 negative.
3 minus. PO4 3 minus. Phosphates tend to be insoluble. Why would a phosphate tend to be insoluble based off of this slide here?
Because it has a high ionic charge.
What difference would that make?
You got me there.
What's up?
Does it have anything to do with that it's surrounded by oxygen already? Phosphate?
Maybe, right? So we could make an argument based off of the individual intermolecular forces, all right? The difference in electronegativity between oxygen and phosphorus, and that's important, right? But I'm just saying based off of what we're talking about right here, right? Right here. Obviously, to answer your question, we can't completely separate those other components, right? But what we can say is based off of an argument of disorder, why would phosphates maybe not be as soluble? Right? What is going on? So remember, I've got some whatever phosphate you want. Calcium phosphate, right? Everyone's favorite type of phosphate. I'm just joking there. Just making sure you guys are out there awake still, right? Okay. And you put that into water. Okay. And those ions are going to break apart to a degree. Why would that not be as soluble though? That's something like sodium chloride. Yeah, what's up?
Well, because each phosphate is going to attach to 3 calciums, right?
Not really. Right? Calcium has a 2+ charge. Phosphate is a 3-.
Okay.
Right. So there'd be a mixture of this stuff together. Yeah.
Okay.
So 3 calciums and 2 phosphates. Yeah.
Since it has that higher charge, it probably wants to stick to its cations a little more.
Aha, perfect. So I like that answer there, right? So remember in the previous chapter, we talked about the higher the ionic charge, the harder it is to break things apart, right? Now that goes into, I don't have it, so the enthalpy of the lattice there, right? It's going to be harder to break apart that lattice because of a stronger charge. So that's something useful to think about, okay? I'm going to go back to a slide here and have you guys really look at it, okay?
But my brain already hurts.
All right. We can use this slide here. Okay. What happens as soon as I put an ion into solution? What happens to the water molecules? Right? They're going to get attracted to it. Got it? Why do I decrease entropy? Why do I decrease entropy when I put something into solution? Because I end up what? Ordering my water molecules around it. Got it? So here I'm showing you a positive charge and all this kind of stuff, right? What would happen? Okay, hang on a second. What would happen if I have a bigger positive charge there? What if instead of sodium, I have a calcium with a 2+, or a scandium with a 3+, or whatever with a 4+?
There's something with the 4+?
There's lots of titanium could be here.
There'd be more order around it
Why would there be more order around it?
because of the higher charge.
The higher charge. You guys with me on this? Think about this for a second, right? So we're ordering the water around there. What if I have a bigger positive charge? A bigger positive charge is going to start to attract more water molecules around it. Okay. Well, we would call this is our first sphere of hydration, right? The immediate waters around there. We'd have a second sphere around that. Okay, that would start to order a little bit more also. Because watch, this is subtle. Do you guys see how these waters are arranging themselves so the oxygen's bound to there, right? What do we have here on water?
Polar hydrogen.
Polar hydrogens. What's going to be attracted to that hydrogen right there?
More oxygen.
Another water molecule. You guys got it? And if this hydrogen's not moving because it's attached to there, what's gonna happen to the water that's attracted to that one? It's also not gonna move around as much, right? Because it wants to stick in place. Okay, so we have these kind of layers. It basically forms an onion, right? You want me to make a Shrek argument
Yes.
here for you guys? No, right? But there's layers of water that form around an ion, and the bigger the charge, whether positive or negative, is going to have a bigger influence on arranging the water molecules the further out it goes. Okay? What's up?
I'm still a little confused
Okay.
on entropy.
Yep.
So is it referring to like water's order?
Everything's ordered.
Everything's ordered.
Mm-hmm.
So we're
We can
saying-
look at, but when, so, not, I don't mean to talk over for you a second, right? But when you want to make an argument from entropy or enthalpy, start to look at an individual part and see what happens with that. So we say, okay, if I just look at the water, it was tumbling around and doing whatever, now it's ordered, right? From the ionic side, it was ordered in a crystal, and now it's in solution flowing around and moving. So we have the opposing parts to it there.
So entropy refers to a molecule's movement in a solution.
It refers to disorder, right?
To not being locked into a particular shape or organization.
Yeah, that might be another way of thinking about it.
Okay.
Now, so that's fine, that's a great definition, and it'll serve whatever purpose we need, but we'll put an energy component to that later also. Okay? What's up?
So does that mean that like pure water is by nature fairly entropic?
I mean, there's more of an order to it because of the hydrogen bonding, right?
Right.
But I don't know. I don't really have a good answer for you. I don't know. I've never studied the individual entropy of solvents, I guess. I'm sure somebody has. I just don't know.
So do solvents typically have a higher entropy than solutes that crystallize? Like presumably something that's locked into a crystalline structure has very low entropy.
Yeah, I would agree with that statement. Yeah.
Okay.
But I think it depends, right? If you're trying to mix two liquids together, we'd have to take a look at the individual measure. You can do that. I just never looked at it. But. Okay. All right. So one last thing before I beat this to death here. Right? So do you guys start to understand how enthalpy and entropy play together here? What am I really trying to bring these arguments back to? I'm really trying to bring these arguments back to these intermolecular forces. Okay. How can I attract things together? How can they influence the things around them? And how can we start to calculate the energy that's gained or lost as we increase the number of intermolecular interactions or not? That's what it comes down to. Okay? You guys with me a little?
Yep.
Does it make sense?
Yep.
So start to think a little bit about order and disorder, and we'll start to play this into some of our discussions as we move forward. Okay? Cool. All right, that seems like a good place to stop. Next time we'll talk a little about how to calculate entropy, and then we'll keep moving through to our colligative properties. Okay?
Think that.
That's what I
I work 15 hours because I'm trying to understand